When we design a gearbox, we need to know a number of things. The first question you might ask is, what speed ratio do we require? That is, what is the input RPM and what is the output RPM? What do we need for the machine to work? That's the output. What do we have to drive the machine? That's our input. What are the torque ratios? Again, input to output. How many stages do we want? A stage is each reduction ratio in the gearbox. And we generally recommend that the gear ratios stay below 10-1. Then, of course, we have to figure out how we are going to align the input and output shaft and where they are located on the gearbox. Once we know that, we can start choosing some gear sizes to meet the gear ratio requirements we have in each of the stages that we have specified for our overall gearbox speed and torque ratios. When we have those gear sizes chosen, are the gears going to be able to handle the loads that we are transmitting through them? And will they do so without yielding? And will they have infinite life? Before we get to that, we're going to do some basic gear trains. And so first up, we're going to show a simple gear train here. It consists of an input gear, which I'm labeling as gear 2, the housing which holds all the shafts upon which the gears are placed is usually labeled component 1, and then we number the gears in the gear train as we move through it. In this case, we have 5 gears labeled gear 2, 3, 4, 5, and 6. Gear 2 is the input gear, and it is spinning at input N2 clockwise. We have a 20-tooth first gear, a 30-tooth second gear, a 45-tooth third gear, a 25-tooth fourth, and a 36-tooth sixth gear. Now, we cannot bring these gears together unless they have either the same diametral pitch or, in the metric system, they have the same module. Those have to be the same in order for these gears to interact. Each gear pair has to have the same diametral pitch or module. So now I'm imagining that I have these gears in this gear train, and the number of teeth on gear 2 is N2, gear 3, N3, and so on. Gear 2 is the input, and it has an input speed N2 as the RPM. So the first question is, which direction is gear 6 spinning? Well, if gear 2 is spinning clockwise, then gear 3 will be spinning counterclockwise, gear 4 will be spinning clockwise, gear 5 will be spinning counterclockwise, and gear 6 will be spinning clockwise. So the direction of gear 6 is going to be clockwise. The next thing we want to ask is, what the heck is the train value? The train value is the ratios of the input to the output speeds. This train value is usually denoted by lowercase e, and it is given as the product of the driving teeth divided by the product of the driven teeth. So in this simple 5-gear setup that we have shown up above, so the driving teeth in this case are going to be gear 2, gear 3, gear 4, and gear 5. We take the product of those tooth counts and we divide those by the driven teeth, gear 3, gear 4, gear 5, and gear 6. And you're going to notice that gear 3 drops out, gear 4 drops out, and gear 5 drops out. All of those gears are called idlers. So they don't figure in the overall train value. In fact, in this particular problem, the train value is just going to be N2 over N6, and that is just equal to 20 teeth on gear 2 divided by 36 teeth on gear 6. And so the train value is just going to be equal to 0.556. And so the speed ratio is going to be given by N6 is equal to the train value times N2, which is the input. You could just call this N out is equal to E times N in this case. And so if N in is 350 RPM, N out, which is just going to be equal to 198 RPM. So the output torque is going to be given by 1 over E times the input torque. So you'll notice in this case, because N2 had a smaller number of teeth than N6, that our speed was reduced, but our torque is going to be increased. It's just going to be 1 over 0.556 times the input torque. So we are going to amplify the torque and we are going to reduce the speed. What that means is that the power is the same at the input and the output. The difference is the speed and the torque associated with the shafts upon which those gears ride. Let's go back to the gear train we were just working on, and let's imagine that this is a system. We know that the diametral pitch of the gears is 8 teeth per inch. We also know that the input RPM is equal to 350 RPM. We had already determined that our train value, N2 over N6, which is 20 divided by 36, which gave us a train value of 0.56. So we know that our output speed is going to be equal to 0.56 times the input RPM, 350. That gives me an output RPM of 198. Now, I want to know what my output torque is. Well, it's just going to be 1 over E times my input torque. But I don't know my input torque just yet. I need to know something about the power input. So let's imagine that our power input is 20 horsepower. So that means I can find my tangential force using the English relationship equation between horsepower, H, and pitch line velocity, V, where I'm measuring the power in horsepower, and the pitch line velocity is in feet per minute. So I need to know my pitch line velocity, V is, and it's going to be equal to pi d n over 12. We know that n is the input speed, that's 350, but we don't know what d is. But we do know that the diametral pitch is going to be equal to the tooth count, which in this case is 20, divided by the diameter, d. And since I said my diametral pitch was equal to 8 teeth per inch, then my 20 divided by 8 is going to give me a pitch diameter, 2.5 inches. Then my pitch line velocity, V, is going to be pi times 2.5 inches times 350 RPM divided by 12, and that gives me 229 feet per minute. Once I know that, I can calculate my tangential force. It's equal to 33,000 times my 20 horsepower divided by 229 feet per minute, and that is going to give me a tangential load of 2,881 pound force. That's acting on the tooth. My input torque is going to be my tangential load times my input radius, and that is simply going to be 2,881 pound force times 2.5 inches divided by 2. That gives me a torque input of 3,601 inch-pounds, which if we divide by 12 is going to be 300 foot-pounds. So we have an input torque of 300 foot-pounds. My output torque in this case is going to be 1 over E times my 300 foot-pounds, and that's going to give me an output torque equal to 540 foot-pounds. So there you have it. We can do some calculations on these gear trains. You need to have some confidence that simple train value equation can work in a scenario that may seem more complicated. So I want to just introduce this idea of this compound gear train. The housing that we attach the shafts to is usually component 1. So we label the gears 2, 3, 4, and 5. And our capital N's are the tooth counts on each of those gears. So in this particular case, I'm going to have an input torque here and an input RPM RPM, and then I'm going to have an output torque up here with an output RPM. And of course, I would like to know what the train value was for this particular system. If we look down the axis of the shafts, we get the drawing over here on the left. When we have these dashed lines, it means we have a gear that's on the same axis. And then you might think, how am I going to find the train value for this system? But remember, the train value is just the product of the driving teeth divided by the product of the driven teeth. And in this case, gear 2 is driving gear 3, so it occurs in the numerator. Gear 4 is driving gear 5, so it occurs in the numerator. The driven gears are gear 3 and gear 5, so that is my train value in this case. And you can validate that if you want by looking at the RPM values at each of those gears, noting that the RPM of gear 3 is going to be equal to the RPM of gear 4 because they are sitting on the same shaft.